Alright. So start with questions from homework. Yeah. 2-2.
Oh, yeah.
Guys, number, which one? 30. Okay. Oh, okay.
I did these.
So this one requires graphing calculator. I'll show you a couple more things when as long as I'm going to put this up here, I'll show you a few things on there.
I work to pay for school.
Right. All right, well, that's warming up. Somebody else have another question from homework? Yes? 20? 2.2? Oh, okay. So this says, sketch the graph of making a table of values. And that's actually related to something somebody came by and asked me about. So the first way we learn how to graph anything is to make a table of values. And the more shapes you know, the less points you got to get, right? So if I know it looks like a U, I just got to get 3 points and then I can fill the U in. Right? And we know what a radical looks like. So maybe just a couple points and I'm good to go, right? But you just got to be smart about what you plug in there. What's the domain of this thing?
0. Equal to 0. Greater than or equal to 0.
No.
Negative 4.
Greater than or negative
Yeah, well, it's got to be true. The inside, you might say that, it might just, it's got to be greater than or equal to 0. And then you solve that and you get. So what do you definitely want to put in your table then?
Negative 4.
Negative 4. You want to know where the hell it starts. That's kind of like the most important point. Where's this thing start? So of course when you put a negative 4 in, you get
0.
It's crazy. Now what's the next good number you happen?
Negative 3.
Negative 3. And you get 1. 1. Now would you put a negative 2 in there?
Probably not.
Hell no. I would not. The square root of 2 is not easy to graph.
0.
Negative 1 sucks. 0 would be the next good, smart number to put in there. So when you make it a table of values, you can pick whatever the hell values you want to use. So pick good ones, pick smart ones. Right? So I'm not going to use negative 2 negative. I'm going to use 0. The square root of 0 plus 4 is 2. Right, and then just plot those points. Is that good? Who asked that question? Where were you? You. Is that okay?
Yeah.
Okay. Damn, that is blatant.
No, it's not you, I promise.
No, it's alright. I'm a math teacher. It's got to be.
No.
No, I don't take that personally. Sorry. You sort of teased me here, projector. It's there. Alright, so I want to do this. This is problem number 30 in the same section.
Oh, perfect. That's
Section 2.2.
2.2.
There you go. Alright, sweet. Oh, I was so hopeful. Such a useful, it's a nice thing preparing my desktop for me. It's so nice.
Yes.
Oh, that's nice. Alright. That's new. Alright, let's see. So let me show you a couple things. Now we'll talk about the problem itself, obviously, which is, if they give you a function, they say graph it in all these different viewing rectangles, and then pick the one that's best.
Mm-hmm.
So how do I change, well, let's put the function in there first. See how that makes sense. No. So if I put the function, you go to y equals, and this one is x squared minus x minus 20. Okay. So far so good. And then I graph that thing. Now, when I first graph this, it's going to be almost anything really, based on what I did before this. It might be a really weird window. So does somebody remember, whenever I put a new graph in, I don't even hit the graph button necessarily. The very first thing I hit is zoom 6. The zoom standard. It puts it into the -10 to 10, -10 to 10 window. So it's a decent window to start with for most things. So zoom 6. So we'll all have the same thing to begin with. Everybody that actually has a graphic calculator so far. Okay. Is this a really good window for this? No. Because we know what this is supposed to look like. Parabola. So obviously this vertex is down further. So in this specific problem, they give me certain windows to use. Now the first window they want to use is -2 to 2, 5, -5 to 5. This is -10 to 10, 10. Is their suggestion going to be good? No. So you could do it, but it's going to be foolish. It's going to zoom further in, and it's not going to be any good. Are you guys kind of with me? Yeah. In fact, if I did it, I wouldn't see a damn thing. -2 to 2 by -5 to 5. I'm going to see this, which is nothing. That's great. Thanks, book. And the next one is the one we already have. -10 to 10, -10 to 10. And then they say -7 to 7. So let's give them a try. How do I make the x's go from -7 to 7?
Type in 7.
I love it. 7. You know, I don't know how to tell you. Just put the 7s in there, Jeff, and you'll be all right. And the y's, we've got to go from -25 to 20. Let's see if this window is any better. That window looks really good. Right? Yes, sir.
Why couldn't you just do zoom fit?
I'm getting there. I wanted to do the problem, and then we'll talk about some extra features. So the problem says to make it these different windows. So you have to know how to work with your window directly. Now, in general, if I come in here and I see this, so this is what it looks like in the standard window. I know what the problem is. The only problem really is I can't see my vertex. And of course, what's the only thing I really need to change to be able to see that vertex? The Y min. So I would just go straight to window and make Y min whatever the hell I want to. Let's make it -20. Why not?
0.246.
And they're almost, see? We're just going to make it a little bit more and I'm good to go. Now there's another thing. There's zoom, like Ryan said, at the very bottom.
0.
Yeah, zoom 0, zoom fit. So if I hit zoom fit, it tries to fit the function in. Sometimes it works, sometimes zoom fit is not good. So I honestly don't use it much myself. But it's not a bad place to start if you're not sure what the hell's going on. Another really good place to go is to go to the table. If you hit second graph, my table looks like this. Your table could very easily look very different. Neato, but you can scroll up and you can do the same stuff. Right. So those of you with calculators, you kind of with me? And the reason we go to table is just so you can see what the outputs are, so you know what to change. So I can see that my y's go down at least to 20, so I can make my y min -25 or something. So I know for sure it'll fit. You got it with me? Yes?
Should we graph that without a calculator?
Of course, yeah. We could factor that thing, do y-intercepts, and x-intercepts, and then get the y-intercept, get the vertex, -b over 2a. Oh, yeah. You got it. But the whole point of this thing is just to get you used to the graphic calculator. Okay. One other thing I want to show you. And remember, this function... Oh, shoot. I still got to get that TA money. All right. Let me give them my TA money. Now I'm going to go here. This function was x squared minus x minus 20, right?
Yes.
Yeah.
How do you find the vertex of this by hand?
-1 over 2a.
Yeah, so it'll be
-1 over 2.
the x piece will be -b over 2a. So be careful. What is b?
Oh, 1.
Yeah, it's negative 1. So negative 1 is 1 over twice 1. So it's 1/2. Right? Is this familiar, hopefully? Anybody never seen the negative b over 2a thing? Be honest. It's okay. It's just not your fault. Your teacher never shows you. All right, I'm sorry. Real quick. Stay with me then. Some of you guys already know most of this, but real quick, just a little review. How do you factor this thing?
X minus 4.
Careful.
X minus 5 minus 4.
Yeah, big one's negative. Good. So its x-intercepts are...
Negative 4 and positive 5.
Yeah, good. Negative 4 and positive 5. Now, what's interesting about a parabola? It's an example of a function that's got inherent
Equidistant point.
symmetry. I love it. So where must the vertex be? If I know these 2 points that are across from each other, the vertex must be
In the middle.
right in the middle. You guys kind of with me? Some of you guys are like, yeah, I've heard this before. That's where negative b over 2a comes from, because these x-intercepts are nice. Right? And what's right in the middle of these turns out to be positive 1/2. If you add these and divide by 2, you get 1/2. And what do we get so far for the vertex? We got x is 1/2. If I would have made one little change, stay with me now. If I would have made one little change to this problem, if I would have made x squared minus x minus 21, why would that suck? Based off of trying to do what we just did.
Because you have to use
Can't factor it, I have to use quadratic. And of course, quadratic, remind me, what is that?
negative
B
b plus or minus 2a.
square root of b squared minus 4bc over 2a.
Let me write it like this, because I can break those pieces up, right? Break them up, each of them over 2a now, right? So since the vertex is the x value, has an x value that's right in between our intercepts, these would be our intercepts, right?
Mm-hmm.
So what would be right in the middle of negative b over 2a plus this much, and negative b over 2a minus the same amount? The thing that's right in the middle, of course, is the freaking negative b over 2a, the thing I keep building off of. You with me?
Mm-hmm.
So that's why x equals negative b over 2a is a shortcut to find the x piece of the vertex.
Makes sense.
Cool. So some of you guys might know this, but maybe forgot this, why that's true, or in somebody, of course, just told me you never heard of the damn thing, so now you know it. Good. Really good thing to know. How do I get the y piece of the vertex?
You just input your 1/2 into
Yeah, just put the 1/2 in. So I get 1/4 minus 1/2 minus 20.
Which equals 20, negative 20.25, or 20 and a quarter. Negative
Yeah, negative 20.25.
25.
I like this number, right? So if I were to find the vertex using something in the calculator better well spit out at me 1/2 negative 20.25, right?
Mm-hmm.
All right, so how do I find the vertex using something on the calculator?
Did you say?
No.
Input minimum.
Yeah, second trace. Oh, okay, I got you. I'm with you. So not trace itself. Trace wouldn't be good enough. The second trace gets you then out. And then in this case, of course, what do I want to use?
Minimum.
Minimum. Because in this case, it's opening up, so the vertex would be the minimum. Cool. So if I do number 3, it's going to ask me 3 questions.
Right.
So right now, I'm right on near the vertex. So I want the left down. So I want to go left a little bit. Enter. And see it opens a little arrow. Right down. So I want to go over to the right of the answer a little bit. Enter. And then my guess, of course, everything's happening way at the bottom here. Enter. And it gives me, and of course, this is good that this is happening. The poor little calculator dude, right? He's not doing an infinite number of points to graph this damn thing, right? He's doing a finite number of points and filling it in with a line. You with me? So sometimes it's going to tell you something like this. Most of the time when you get something like this, it's desperately trying to say 0.5. Especially because we already know the answer is supposed to be 1/2. So this is just resolution problem. It says that's close enough and stops. You kind of with me? Okay. All right. So if you have a problem where, you should have seen these kind of problems before where we have the profit function. And a profit function normally looks somehow related to this. Because there's the promised land, right? I want to move closer to here so my profit is as much as it can be. So of course the quick way to do that is to graph your profit function and then do the maximize function on the calculator. And you can find how many widgets you got to sell to get the maximum profit. Cool. Okay. Good. And real quick, let me show you a couple other little things real quick. To find these roots, and we already know it's supposed to be -5 and 4, or -4 and 5. How do I find them using the calculator? How would I find this root right here? Second,
0.
cal, and then the 0. Good, because the 0 is the 0 of the function. It's when the output is 0. That's going to be the x-axis. So if I go to the 0, it's going to ask me 3 questions. It's going to say, what's the left bound? Let me pull this parabola up a little bit so we can see it a little better, all right? Because all this stuff is in my way. And the way I'm going to pull it up is by actually pulling y-min down a bit. So that pulls my bottom up a bit. Is that high enough, Jeff? No. Screw that. Let's make it -30, and I don't know why this is freaking 9. Oh yeah, I did zoom fit. Alright. That's a little bit better. Oh yeah, that's right, I'm way up here now, so that's cool. So if you go to second, cal, 0, go to the one you want to find. It's going to say left bound. So what I always tell students is get right on top of it and then hit the left arrow a few times, enter. Get right on top of it and then hit the right arrow a few times, enter. And then this is kind of like where the calculator is going to look. So if you go back a bit, enter. Okay. And I'll tell you this, if you get into, now a lot of you guys are going into Math 180, you will learn the algorithm that the calculator uses to do what we just did. You'll be able to do it by hand.
Whoa.
Dude. Right. It uses some calculus to figure it out. Really nifty.
So that's a test
Okay, I like that. That was a major reaction.
So that would be a test problem.
That would be a test problem in Math 180, is become a graphing calculator. All right. Anything else while I got this up here? Any other burning questions about graphs and stuff?
I was just wondering, so the vertex part of the column, that was part of the homework? Okay.
No, I think
I
I
was
just
just
made,
wondering.
yeah.
Okay.
The homework is just very simply do these windows and tell me what's best.
Okay.
But I want to give you a little,
Insight.
as long as I got this up here, give you a little bit more. Okay. So anything else from homework stuff?
36.
In 2-2? 2-2 is a rough section. All right, let's see. So we got a piecewise function here. So 36 gives me And let me say this real quick. For those of you guys who are doing WebAssign, feel completely free to bring a printout in and ask a question from WebAssign. Don't feel like you're going to be left out of this homework question and answer session. Right? Bring the printout in. You can bring it up to me. I can copy it down. What the hell? It's fine. So this one says, what does this one say? This one actually wants me to graph it. So how the hell do I do that?
Tables. 2 tables.
Cool, and in fact, this one is kind of nice. What's going to happen starting at -2? Can somebody draw in the air what it's going to look like? It's going to be a flat line. It's going to be 5, right, forever. So if I make a table for the first dude, and what's the first little number I maybe want to put in there?
We're doing 1 minus x.
2. And you guys see, what does it say?
X is less than -2.
So this is only this when x is less than -2, but I'm going to be crazy. I'm going to put...
No, you start with
I'm going to put
-2.
-2 in there. You can't do that. But of course, we say we put little parentheses around, makes it legal. But officer, I had parentheses around. And of course, hopefully this makes sense. I got to know where to put that open circle.
Yeah.
So I have to know where it would want to be, right? So I'm going to put an open circle there because it's not really part of my domain. So when I put a -2 in, I get crazy. And then I can put in, no, I don't need a parentheses anymore. -3.
4.
And I get 4, yay. That's all I need. It's a straight line, right? I just need a couple of those. So now I've got a -2. Interesting things are happening. And -2, this tells me it's 5, closed circle because I'm allowed to equal it at -2. And then it's 5 forever in which direction? Yeah, above that, so up from there. Now, this part at -2 wants to be at 3. We can't let it be there, so we put open circle. And then at -3, it is at 4. So then it's a straight line from there. Why does it make sense? The line's going like this? Because the slope is negative. Yeah, good. So you got these little things you can check real quick to make sure that it makes sense what you did. Line's going down. It's got negative slope. Good. Does it pass the vertical line test? Everything?
Good.
Well,
It better. It's trying to say it's a function, right?
oh yeah.
Yeah, 'cause it's not.
It does. Because right here,
Yeah.
it's fine. It's there, not there. So it still passes. It only goes through once everywhere.
So, if they would ask for interval notation, how would you write that?
Oh, for the domain and the range.
Yeah.
Okay, so if they did, I don't think they do, but it's a really good question, because you know I'm probably going to do it. I think they did that somewhere else. They asked domain and range for piecewise. Domain is definitely going to be, yeah, pretty much gives it away here.
Yeah.
All the x's down, all the x's down, it's every freaking thing. So it's all real numbers, or all real numbers, or just write all real numbers. And then range, good, the lowest, now be careful, careful. Good, yeah. The lowest output is almost 3. So almost 3. And it doesn't miss anything after that, right? To infinity. It just happens to have an infinite number of 5s, but who gives a shit? It just hits 5 somewhere. That's all we care. So it goes from 3 up. Yes, sir?
What if there's, on the circle, the open, what if there's both an open and a closed? Is that
Then it's really just a closed.
Is it really just part?
Because one side wants to be, the other side says I could be. Then it's
So
closed.
that's why it's all real numbers on that one?
So again,
Is that why it's all real numbers on the domain? Or I'm confused on why it's all real numbers on the domain.
because there's no x value that does not have an
okay.
output.
Okay.
Let me say that without a double negative. Every input has an output. Therefore, the domain is all real numbers.
And that's because it's a straight line and then that line continues on in that
Yeah,
direction.
every single x value can find an output somewhere.
Okay.
Yeah,
I get it.
I like it.
So there could not be only one. More than one on this one.
Stop it. It's a function. So don't.
Don't confuse me.
Every x has only one y. That's why it's a function. But why is the domain all real numbers? Because every x has at least one output. Yeah.
Because number 40, it can't have at least one output. It has one output.
Well, the second statement I made had nothing to do with it being a function. It just had to do with it having a domain of all real numbers. You guys are awesome. Let's bring semantics into math. Why not? So is that any other questions on this here? If this line would have been pointing down, my range
It would have been different.
would have had a hole in it, right? I would have had to do something union something.
Okay.
You with me? If this would have been pointing down, can you guys imagine that? This would have been like that. Then nothing here, none of these outputs exist. We had one like that before. We did one like that before. So my range would have been 2 separate sets from infinity, negative infinity up to here, and then from here, well, and then this. That's it. Really, I forgot this doesn't go up. That's it from negative infinity to here, and then 5, and that's it. That would be my range. Cool. But I didn't do that. Maybe. So somebody else had a question, and then we'll do some new stuff.
I
Yeah.
said the last two from 2.3.
Oh, 2 for, okay. 2, 3. The last 2. Help me out with that. I don't.
51 and 44.
Thank you. Oh, Stefan Boltzmann law, yeah. Okay, so I think on this problem is just the numbers you get are very small, right? So part A says graph the function, and it's got a little. All right, so okay, so you could do this by hand. You would just have to be careful with your scale. If you try to do this in a graphing calculator, you still have to be careful with your scale. And how do I know that the outputs are going to be so stupid small?
Because of the 10 to the negative 8.
Yeah, 10 negative 8, right? So I'm going to get really stupid small outputs. So I'm probably going to want my Y scale, my Y min, Y max to be very small so that it kind of blows it up so I can see what the hell's going on. Okay. And that's all I'll say. I want you guys to try that one out on your own based off of the simpler example we did together.
You know, when I did this, the numbers didn't necessarily come out too small. I mean, it started small, but it grew quickly.
Yeah, and this, they don't give us a range over which this works.
100.
But, yeah, okay, there you go. So they want us to graph it between 100 and 300. Oh, it's to the 4th power, that's right. Yeah, then you'll be fine. It's not even as hard as I thought it was. You'll be fine. You just got to make a little table. You don't even have to do that. It's a graphing calculator. I keep forgetting. I'm not even going to talk about that problem. Just make the graphing calculator do it for you. So you would put in a y1, you would put the 5.67 times 10 to the negative 8 x, right, to the 4th. And then you would make your x min and x max, what?
100 and 300.
100 and 300, because they told you that's what they want you to graph it over, right? No problem.
WebAssign's awesome. That's a problem in WebAssign.
Huh?
That is a problem in WebAssign, but it gives you like 4 different graphs to pick from.
Yeah, I know. Yeah,
It makes you pick one and then you
I know.
see whether it increases.
That's one of the downfalls is from a teaching perspective is there's not enough open response.
You still have to put it in the graphing calculator.
Yeah, but you
And I
get to
actually
pick.
got it wrong the first time.
Oh, okay. All right. Well,
Simply because I didn't the scale.
any other real quick questions before we? Oh, you said the last two.
Well, I think that the same thing
Kind of similar.
makes sense.
Exactly. So now you just plug that in the graphing calculator. And find the temperature where it's a minimum. So you have to kind of play with the window until you can see the
Yeah, that wasn't
see the bottom.
That wasn't
Yeah, but the thing that it kind of gets you at is where it talks about the volume in cubic centimeters, not 1/3. You gotta convert it.
Whoa.
No. So you got to be careful. Cubic centimeters is a measure of volume. Kilogram is a measure of mass. Right? Well, in water, they actually end up being the same. We won't get into this whole thing. Yeah. We'll leave that alone for now. You don't have to know all that. Don't worry. It's not a unit problem. Don't worry about it. It's just a purely, can you graph this thing, and then can you find the minimum? And they give you between 0 and 30. So you would make x min 0 and x max 30. They give you everything you need, right? So in my day, we didn't have graphic calculator, so that kind of problem I'm not going to say much about. Nowadays, it should be easy. Okay, so let's get into 2. So last time we did 2.4.
And we started 2.5.
We just barely got into
We
2.5.
didn't talk about stretching.
Stretching is important.
And shrinking and hot and cold.
I always called it stretching and compressing. It's kind of make more sense. Let's see. So I think the first thing we did was just shifts. So remember last time we talked about if I'm given a function f of x. I'm given some function f of x. What would this do to it? Let's say that c is greater than 0. Is that cool? So I don't have any hidden things here. C is a positive number, so we'll take it to the left. C steps, right? Let me just stop right there. So if I had square root of x plus 4, it would be this shape picked up and moved left 4. And then you just put it back down. Right? That's all transformations are. So if I had f of x minus c, that's right, c. If I have f of x plus c like that, up c. And if I have x minus c that's crazy, that would be no. Okay, that's what we talked about last time. I think we talked a little bit about reflections too, right?
Yeah.
So we talked about reflections. No, Jeff, the F first. There you go. So if I have the negative on the inside,
Across the line.
good. It's going to affect the domain because it's with the x. So it's going to, if I have a square root of negative x, it would take the square root of x and it would just flip it around the y-axis. So this would be a reflection around the y-axis. So how do I reflect around the x-axis?
You make the line negative.
Yeah, put the negative where?
Well, you're outside.
Outside the function. Good. This would be around the x-axis. Cool. So a little example. Last time we did square root of negative x. And you see, it's got to affect the domain, which will affect the left and right swing, right? It'll swing it around left to right because it's in with the x. So my numbers I plug in, they now have to be
Swinging at the
the numbers I plug in. They have to be what kind of numbers? Negative. So the negative is positive. So that's why this ends up looking like that, roughly, right?
Mm-hmm.
Just take that radical and swings it around. This guy would take, if I have negative square root of x, it would take this and just swing it down. And I think it's the very last thing we did was that exact problem. All right, how are we feeling so far?
Feel good.
I'll tell you this. Make a good note of this. Any graphing in this class, I already try to make a big deal of this. I've got to see the detail. I've got to see the scale. And if you're anywhere near as messy as I am, get some freaking graphing. Right? Print it out from the internet. Go buy a pad of it. Whatever. Get together and buy pads of it and distribute it. I don't care what the hell you guys. Secondly, what was the second thing, Jeff, you could do? Oh, specifically for these kind of things, transformations. What I will say on the quiz or a test is I'll say list the transformations, and then you have to show me the dotted line that's the base function, and then you got to show me how it moves around. Are you guys with me? So we'll do a problem like that with actually, we'll do one with several shifts in it. Let's do one right now. Yeah. Before I introduce the other shifts and transformations. So if I give you not yummy.
You just want us to graph that?
Yes, we're going to do it together. Don't freak out. But what would order operations say?
Take the 4 over.
Not trying to solve or anything, but like if I had a problem where there's an actual value in here, do inside first. So see, the shifts you do actually follows order of operations. Let me say that again. The shifts that you apply, because do you take it up 4 first, or do you reflect? Do you do that? Follows order of operations. Now, sometimes you could, and there's some you could do either way within that, but just to keep it really straight, because I definitely want to do this last. So I would apply this shift first, and what's that shift?
To the right.
Good, right one. So I would take that right one, then what am I going to do to it?
With the negative on the same side.
Good, reflect across the x. Good, I love it. Kicks ass.
You can go up 4.
And then the final thing I'm going to do is I'm going to take that up 4. All right, so let me show you. So here's pretty much what I want to see. Okay, so let's see. So I've got my base function. My horrible scale. Awesome, Jeff. All right. Where am I at? Okay, so my base function would be 0, 0, 1, 1, and what else?
4, 2.
Because what is my base function? Take all the shifts out, and of course I'm left with square root of x, right? Everybody cool? So if you can identify the shifts, you should be able to realize what it looked like before those shifts were applied. Are you guys with me? And that's what I want to see first. That's the dotted line I want to see first. Is what's the base function before it's moved around. So that would look like 4, 2. That would look like this. Now you start moving it around. And this is where my anal retentive students are really appreciated because they crack out the colored pencils and stuff. It's awesome. Right? And students like me are just like, so the first thing you want to do, to the right one,
Upside down.
right? And then this goes to the right one, and then this goes to the right one. So that's the first little shift, right? And then what? Reflect it around the x-axis, so this is not going to go anywhere, right? This goes
Down.
here. This goes... Oops, why did they go... Oh, yeah, that's right. This goes here. How are we doing so far? So this was shift... this was transformation 1. This is transformation 2.
And you want us to show all of these?
Well, you can kind of do 2 at once, as long as they see the base graph and then some idea of how it got to where it gets. And of course, why is that? Because, I'm not going to be able to keep those graphic calculators out of your hands forever, and I need to make sure that it actually came from in here. And then the last thing is up 4. So the colors is too bad for me. So up 4, 1, 2, 3, 4. Up 4, 1, 2, 3, 4. And then up 4, 2, 2. So it actually hits right back to where it was. It's awesome. So what point is this? 2, 3. So is that true? Is that a point on this graph? 2 minus 1 is 1. Negative square root of 1. Negative 1 plus 4 is 3. Yes, thank God. That's how you check yourself. Because that's what's supposed to happen, right? Everything that this graph goes through is supposed to work in its equation. That's the connection between the algebra and the visual, right? That's how you check yourself at the end. Questions? Some of you are looking at me. You have a question? Or...
You want us to show all this on tests?
Yes. Somebody else want to ask that same question?
Well,
Somebody else, you don't want to show us some of the tests?
Nice.
yeah, I like that question.
Yes.
How did you know the points that you need?
Oh, so again, I tried to make a point of that when we were doing the graphs last time, talking about my anchor points. So for a parabola, then I have to shift my anchor points to be 0, 0, 1, 1, and negative 1, 1, right? And those are the 3 I would move around, and then I could just put the shape back in. So if you have your anchor points, and then you move them around and reflect them and all this kind of weird shit, then you can just fill the shape back in. So my anchor points for this were 0, 0. The square root of 0 is 0, square root of 1 is 1, square root of 4 is 2. So that's were my anchor points. And then I just move those points around. It's a hell of a lot easier than like, how the hell am I going to move this freaking shape around? No, just look at the points and just move them around and then fill the shape back in. Y'all look very concerned, yes?
Well, the only reason I was asking that actually is because, like it'll say, like on the homework, it said, suppose graph of f is given, describe how the graph of each function can be obtained from the graph of f. But when I click the watch it on the video or whatever, because it was talking about stretching, they just say because of where things are placed in the equation, you can just make the assessment instead of having to graph it itself.
No, of course you can. If the question is just, I mean, that's what we did here. That's the answer to that question here, right? How would these affect the graph? We listed them.
Yeah.
Now, if I say graph it,
Oh, that's what you want. Okay.
using those transformations, right?
And you-
So if the question here was how do all the transformations here affect the graph, bam, 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 done. Next problem, please. But the question here was graph this damn thing. So you get bam, 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 not done. Go show me how they move it around. Yeah.
So all of the transformations are dotted except for the last one?
Yeah, the last one is the actual function. Good. So this is where I start, in the middle of things, done. Sweet. And you could apply, I mean, if there was a shift over and a shift up, you could do that all at one time. You with me? If I had to shift this over 1 and down 3, that could be one thing. Are you kind of with me? So you could combine some of these. You don't have to show me like 18 little dotted shit all over the place. I mean, I think that's what some of you guys are getting in your head. No, you could do some of these several steps at once. Just don't do bam, and then answer. I'm done. No, you got to show me something in the middle that shows me how you got there. Aw. Okay. So sympathetic. You guys can do this. Okay. Let's do another one. And then we'll talk about stretching and compressing and all kind of stuff.
Yeah.
So what about... Shouldn't be too bad. Here, you guys try it out on your own, and then I'll come in and we'll see if we agree. And real quick, just based off of what I said earlier, there will definitely be entire tests where you can use your graphing calculator, but you can't use it unless I specifically say use it to do something. I want you to do it by hand, but then you can always check the damn thing in your graphing calculator. That's beautiful. There's nothing wrong with that. The base here was just without the x.
Yeah.
Because the square root of 1 is 1.
Yeah.
So here, if I take out all these shifts, you gotta be careful, this one's 11. Yeah, that's right. It's minus the the x is minus the x. See how this is minus 1?
No, I'm still making my graph.
So the base function here, if you take the 3 away, take the negative away, take the 1 away, you're left with absolute value. And what is that one? If you graph absolute value,
The first thing is
what shape does it take?
minus 3.
Yeah, so it's not round, it's not curved, because the power isn't different than 1. It's the first power, it's going to be lines. But it's a line that has a turn, because you can't go negative. So you know it looks like a V, and then you can just move that shape around. So what are my, oh. Good. Is your angle point 0, 0, 1, 1, negative 1, negative 1, 1. That'll be good. Good. The whole thing was 3 of them. Alright, so what's my base function?
That's
Absolute.
absolute value.
Absolute X. And of course that looks like a V, and your base and your anchor points would be 0, 0, 1, 1, negative 1, 1. So I would try desperately just to have 3 anchor points at most. Because the shape is known. I don't need more than that, right? Okay, good. So it's the same thing we just did with the radical. Same idea. And now, what are my three transformations here?
Right 3.
Good. Do inside first.
X-axis.
Yeah, cross the x-axis.
Up 1.
And then up 1 only. Alright, and then, let's see here. 0, 0, 1, 1, negative 1, 1. Here's my base function. Trying to be. Then I apply my shifts. Right 3. So 1, 2, 3. 1, 2, 3. 1, 2, 3. Across the x-axis, right? So I'll just take this image and just flip it down. That stays, that goes down. So now it's there. And the last thing I do, take it one up, so this will go here. Where am I at? This will go there, and this will go there. Freakiness, right? So this point here is
4-0.
4, 0. Does 4, 0 work? It sure does. Yeah. 4 minus 3 is 1, absolute value 1, negative 1 plus 1 is 0. Kick ass. So you can always check it to make sure it looks right. Of course, how do you graph this in the graphing calculator? Does everybody know where their absolute value function is? Yeah, go to math. Math seems like it would be really useful budgeting. And then go over to num. And the very first thing is absolute value. So if I go to y equals, I can put in there negative, math, num, negative absolute value of x minus 3 plus 1. Zoom 6. All right.
Oh, yay.
Guys with me? I love some of you guys look at me with these really super quizzical, and then you don't say damn thing. I love it. Or you say that. Merry Christmas.
No. Nothing. It's good. I'm fine.
Oh, you got the, oh, cool. Some of you guys, you got the one where it actually shows you absolute value symbols? All right. Only I would get excited about that. Huh?
Old school.
Old school, I like it. Yeah, just leave that. Sweet. All right, how are we doing so far? Is that good? So let's talk about the two weirdest ones, which actually aren't nearly as bad as the book makes them sound. The book defines them as vertical shrinking and stretching and horizontal shrinking and stretching. And what I desperately want you guys to realize is what carries us through this whole thing. This is a minus. Why the hell did we go right 3?
Because it's connected to the...
Because it's in with the X. It's kind of the shortcut. If it's in with the letter, it's got to do the opposite of what it says, right? I like it. And this was plus 1, but we actually went up 1 because it's outside. It's not in with either of these letters. It's going to do exactly what it says. Let me let that sink in for a second. Is that cool? That's how I tried to introduce it the other day, because that'll get you through this stretching and shrinking business. A little bit easier. You don't have to remember horizontal and vertical. Oh my God. So let's try some basic ones that just have these things happening. So
y equals 6 f of x. I already did that problem. That's fine.
So some problems are going to give you...
Well, this one it says, the actual problem is y equals 6 times f of x minus 2.
And what's the instructions?
Well, that's where I'm supposed to just describe how the function...
Okay. Yeah. All right. But let me start with something specific.
One half.
You can do it, Jeff. There we go. Let's just do that. We'll incorporate your 6.
There you go.
Don't worry. The f of x, I made it specific. The f of x here is square root of x. All right. So Ryan's problem there, and you guys probably have something like that in the homework, is less specific. It says any damn function I put here this will have the same effect. Let me say that again because this is important. I don't care what base function I start with. Square root here, all of these would be the same, right? The transformations and the shifts and all, they don't care what the function is. They'll attack any function the exact same way. That's kind of nice, right? I don't have to memorize something for square roots and something for param. They all are affected the same exact way. And that's why they can just put an f of x there. You can say what it does. In this specific instance, is that 6 in with the variable somewhere? No, it's on the outside. So it's going to directly do 6 times what the values used to be. So my base function obviously is square root of x. This is my base function, so it would start off as 0, 0, 1, 1, 4, 2. Okay. I try to want to get that to the point where it's boring. That's cool. You can just do it real quick. That's the base function. And then all I do is I take all the output values and and that's why you can see, that's why they call it stretching. And that's why they call this vertical stretching. But it doesn't matter. Do you remember it's called vertical stretching? No. It's outside. It'll actually do what it says. It'll multiply by 6. So now this output was 1. It's now going to be
6.
1, 2, 3, 4, 5, 6. This output was 2.
No,
It's not going to be 12. So now this thing is going to look like, wow. Yes, sir.
So to compress it, would you multiply by a fraction?
I love it. It kicks ass. If I want to compress it, I don't want it to grow as quickly. So if it was here somewhere, I want to make it half as tall maybe. That'll be somebody sitting on the damn thing, right? Compression. That's why I like compression better than whatever they call it. I can't remember. Shrink. That's stupid. Compress. You can think somebody's pushing on it. So if I wanted to take the square root, I said this square root thing is just too freaking cocky. It goes up now. I wanted to get 1/4. I want to push that damn thing down, right? So again, the base function again is radical.
Negative 1/4.
No, I'm sorry. That's just 1/4. I just want to focus on that. And then later we're going to combine every damn thing.
Okay.
Yeah, you should have known that was going to happen. So now what this is going to do is, and this is why they call it compression, you don't even have to think about it like that, though. You don't need to think about it like it's compression. You just think it takes all the outputs, what they used to be, makes them 1/4 as big. So this used to go to 1, now it goes to 1/4. This used to go to 2, now it goes to 1/2. So this poor little thing was growing really slow already, and we just pushed it even further down, right? We stop right there for a second.
So the inputs are the same, but the outputs are different.
Exactly, because
Okay.
if it's outside of the x, it's affecting the outputs. I don't know if you've noticed that. So like that +1, it affected the outputs. All the outputs got 1 bigger. If it's inside, it affects the inputs somehow.
You just had to say that so I understood.
I got you. It's always a question of, have I said that yet? Have I said it that way? All right, so what the hell happens if I have some of the stuff inside? So let's see. Let me take this here away. Yeah, let's do, what do I got? Yeah, we might as well do this here. Square root of, sure. So remember. If inside I saw square root of x minus 3, is it going to do what it looks like it does? It's not going to go back, it's going to go right through. It's going to go against what it says. So if the first thing I do is double my inputs, all my inputs can now be half as big as they used to be, right? So if I put a 2 out here, it would make everything twice as big. If I put a 2 on the inside, it makes everything half as big, because it's the same idea. It does the opposite if it's in there. Hopeful. Because real quick, this would be y equals 6 radical x, right?
Sure.
This would be 1/6 y equals radical x with me. If it's with the letter, it does the opposite of what it looks like it does. Mm-hmm. That theme carries. And the reason is because what I just said. This is doubled, so all my inputs have to be half as big to have the same outputs. That's why it has the opposite effect. Good. Yes?
The base function would still be
Yes, good.
square root of x.
Base function doesn't care what the hell that number's doing.
So you could
Base
just-
function is radical x.
So you could just put in 4 and then 1, then another 1, multiply it by 2.
So here's if I say use transformations to graph, Let me say this. You didn't mean this, but it made me think this. I don't think you did. I don't want to see any damn tables anywhere. If I see tables somewhere, if you have to use a table, do it somewhere else and don't show me that paper ever. Right? You should be able to get your base points and then move them around. That's the whole point. I don't want to see tables anywhere. I'm not sure what you're asking though. Maybe that's not what you're asking.
Like, you just plug in a number and then just multiply it out and just start.
No, because that would be sort of like making a table, I think you're saying. Plug values in. I don't want to see that. So I know this is 0, 0, 1, 1, 4, 2. Okay, yeah. I had a class where every class started with my teacher, we have a group, and we have an element. I mean, every class. So I kind of relived that with you guys.
Thank you.
I have to spread it along. So since it's in with the x, it's not going to double it. It's going to cut all my inputs in half. Now, notice I was very careful. It's going to cut my inputs, because it's with the inputs, in half. So normally 1 would go to 1. Now 1/2 goes to 1. Let me let you guys absorb that. And is that true? If you put a 1/2 in, what do you get?
A 1.
Square root of 1 is 1, yeah. So if it's outside, it's going to affect up and down. All my inputs stay in the same place, didn't they? My outputs just moved. If it's inside, it affects left and right. All my outputs stay the same, it's just my inputs move. Right? Yes, sir.
So if it was x divided by 2, it would exceed.
Yes, good. Let me finish this out. So this one is, oh yeah, this is a 1/2. Let me not even put that there. It's freaking me out. So that went to 1/2. This was 4. Now it's going to be an input of 2 gets me to 2. I like it. Now, does somebody notice something interesting about this? How does that kind of relate to what we were doing there?
It's like, it's called, well, that's horizontal compression, but it's also vertical.
Exactly. If I compress it this way, at the same time it looks like it's being pulled up this way. Are you guys with me? Because how can I rewrite radical 2x? I can write it as radical 2, no Jeff, 2, radical x. And wouldn't this be this kind of thing because it's on the outside?
Yeah.
It would be a growth in this direction by rad 2.
Yeah.
So that's why if you can pull something out of a function, you can actually look at it either way. So if I had rad 4x, 4 of course will be easier to use here. If I had rad 4x, I can either look at it as doing what in the left and right direction?
Horizontal compression.
Compressing it, shrinking it by 1/4, right? Or what can I take out of there? Rad 4 is
2.
So I can accomplish the same effect by stretching it 2, up and down, right? Stretching it up 2.
You said we're not, it's compression is simply shrinking, is that?
Yeah, compression is the same as shrinking.
Okay,
You
I'm
can
just
see
making
why.
sure, 'cause-
Just to me, compression, I can actually imagine somebody pushing down on something. Especially when we get to trig and we start doing all the same stuff to these functions that look like this. It'll make a lot more sense because you can imagine a spring, and so what do you do with a spring? You compress the spring, so then it makes more sense. If I have a spring like this, and then I want to compress it, I just put a number inside, and it's going to look like that now. Wow. Right? Somebody compressed that spring. Yes, ma'am?
And isn't that technically still correct now? By doing that?
Yeah, totally.
You would be fine.
If you did it, it's just the way we look at it is different, but if I looked at it this way, which would be a 1/4 domain change, right? It would make all my domain almost 1/4 as big. Or if I looked at it this way, it would double all my outputs. The picture comes out exactly the same. The math is the same. Just the way we look at it is different, but the answer's got to be the same. Yeah. How are we doing so far? Okay, all right. So that's the complete picture. So I wouldn't even think of the words vertical, horizontal at all. I think in terms of it's inside, it affects the domain. It's outside, it affects the range, right? I don't have to think horizontal, vertical. That just makes more sense because that relates to what we were saying earlier. Okay. How do you guys feel about that? Is that?
So shrinking vertically, if you're thinking about it that way, would be?
Compression.
Yeah. Well, if you want to shrink vertically like this, so it's compressing vertically.
Down, bringing it down.
Yeah. It would be the same thing as stretching
I got it.
horizontal. Yeah. Okay, but do you have to even think about it like that?
You do if I do.
It's just interesting that that happens, but don't feel like you have to think about it that way. You don't. Let's do one more. I get a feeling that maybe one more is a good idea.
What if, when the fx is in the equation, the function is in the equation? If we do an example like that.
I don't want to. And the only question is, what is it doing? Like the one you were asking earlier?
Well, I mean, yeah.
Okay.
Because, like, what if it says y equals 8 minus the 6 times the function?
Y equals what?
8 minus the 6 times the function. Do you solve for y, essentially, so you can remove it?
No, what they're trying, and I don't even like this representation. They just should just say that. It's just a little bit. There's like 2 y's in there. It seems,
that's
right?
That's why I was.
It's not. They're trying to say like they really should say that.
Yes.
A new function built off of this old function. So what does this new function look like compared to what this looked like?
Oh.
So really, the first thing I would do with this to make it look a little bit better is you know, like ground shaking, but that actually makes it make a little more sense. So this shift would happen. You can even think of it. You know, it doesn't matter what order you do. There's 2 shifts and 2 transformations in there, right?
Yeah, reflection.
There's a reflection around.
X. Y.
No, I haven't.
Don't question yourself. Just because I look at you doesn't mean you're wrong.
Exactly.
Yeah, you just didn't say it very authoritatively. Yeah. Thank you. So it's not inside here. It's outside. It's going to be up and down. So it's going to be either. It's going to be a shift around the x-axis. Reflection. And I'm going to put a 1 here also because they're tied. It doesn't matter which one you do first. So you reflect it
Or you expand.
Good.
Stretch it.
And stretch it. Yeah. Up and down. You can say vertically or whatever. Right, it would make all the outputs 6 times as big, but if you reflected it, it's still going to make them 6 times as big. That's why it doesn't matter which one you do first. And then the last thing you definitely do is up 8. Yeah. Cool.
So if that's if it's a function of x, then that would technically be your y inputs, right?
Y would be the output. If it's a function of x, it means x by input.
They're just doing that as a variable.
So what they're doing, and again, that's why technically they should have written this. I'm making a new function based off of the old function. So this is a very strange. We've never seen a statement like this, really. We haven't, and then I didn't necessarily want to show it to you yet. We will definitely, but you can make a new function out of an old function. That's basically what we're doing. When I say the base graph, this is f of x. So in this case, h of x would equal what?
Your new y.
No. I want specifically.
The square root of 2 f of x.
Oh. Careful. F of x is radical x.
Okay.
So 2 rad 2x. Or
So
rad
h of x would be f of
Oh,
2x. Get you guys with me?
Yeah.
So that's how I could represent building a new function off of some base function.
Like the next problem down in the homework, it says.
Right? So that's what this means. It says take some old function, any function you want. I don't care what the hell you use. Absolute value, square root, cube. Do this to it and then add 8. It's going to make this happen. Yep.
For up there, it looks like if I looked at that, I would think of it being 2 rad x for some reason.
So now stay with me. If f of x is rad x, and I said I had a function that was you mean this looks like it would be 2 rad x?
Yes, that's what I was trying to say.
All right. If f of x is rad x, what's f of 2x? Where do I put this?
Inside rad x.
Which is the function we had, right?
All right, it just looks like.
If I wanted 2 rad x, if I want to get this,
Yeah, well,
F of
Be f
x.
of 2.
f of x is rad x, so I just put a 2 in front of it. Yeah.
I get that.
Because what does this say? It's double the old function. So it's double the old
Yeah.
function. What does this say? It's twice the input of the old. So it's twice the input in the old function. Yeah. Okay. Okay. Mind put up.
Oh, no.
Okay. Maybe it's good to focus on that for a second. So if I have f of x equals x cubed, I have g of x equals -2 x minus 1 cubed plus 7. How can I write g of x as something to do with f of x?
How you got
You
to
understand?
that from
Yes, yes.
that? Okay, that's actually the question I was going to ask you.
I love it. I had a feeling.
That's the next question.
Does that make sense? You understand what I'm saying? It's hard to kind of represent. I want
Okay.
write something in terms of f of x that shows me how I would get this from this.
So you start basically, what is x to the third is your base?
Yes. Cool. So I start with a cubic function as my base. You're looking like, save me. This is weird. I don't feel like you're supposed to understand this all of a sudden right now, right after you first start talking about it. This is weird. We're not used to doing this. We're not used to actually building new functions out of old functions. Even though we've done it before, we never wrote it down like this. So what's the first thing that happens to f of x?
It's
Minus.
so f of x minus 1. Then what's plus
And now what happened to the cube? Well, the cube is what f of x is, right? So don't feel like you have to put a cube there. You're not just throwing an f in the middle of everything. And then actually the funny thing is,
what's y by -2?
They need to put it
What's it?
yeah, so the really important piece is how the input changes. And then everything else is actually outside the function, right? That's nice. I mean, maybe. So if f of x is the cubing function, this says -2 times the cube of this. Well, that's what that would do, isn't it?
Yeah.
Plus that, wasn't it? Okay. So the only thing you really have to worry about is capturing the new input. Just throw that into the old function, you're golden. That's what we did here, right? The new input was 2x. So that's why it's f of 2x. Just capture the new input. Okay, good.
Yeah, but
Yes.
if you do the -2 f of x and you have to input the x cubed, wouldn't it just be x cubed minus 1?
No. If f of x is x cubed, what's f of x minus 1?
X cubed minus 1.
No, hell no. Where do you put this?
Inside.
Where the x is. This doesn't say I cube part of this. This says I cube all of this. So I cube all of this. Yeah, good. So if you have any trouble with function notation and so forth, obviously this is going to be even worse because it builds on that.
Awesome.
I love it. Okay. All right. Let's see. Where am I? Ooh, I love. Look on page 185. So where is it? What I'm talking about? Oh man. Almost out of time.
Where is the last one?
Yeah. Now you see why earlier I was trying to go a little bit quickly. But you slow down.
What?
You had to turn the thing.
That doesn't really bother me.
Me too. All right. Oh yeah, thank you.
I used to hate it, but like now I'm like,
So technically, wouldn't it be the other way around now?
What's that? We do this real quick, Chris. Because we're almost there. And then I'll.
Yeah, I'm not quite grasping.
One thing I like about the new books, or a lot of the old books is they got a little history next to it. I know a lot of you barely read this. You probably don't read that, but
That's my favorite part of the book.
okay, good. Thank you.
No, I'm serious. I just want to remember.
It's where the interesting thing. These are the actual people that did stuff in math. And if you look at the history of math, there were duels and people killing each other and poisoning each other and stealing each other's work. I mean, it's actually very interesting. You could actually make a decent movie out of it. It'd be interesting, to believe it or not.
what would you call the movie so people would watch it?
Yeah, Nick Cage would be involved there somehow, obviously. So here we have what's called a sawtooth function. And if you do any sound work, this might look familiar. So this is sort of getting into like trig a little bit, so trig would be curvy. So here's f of 2x. So that would take that function and it would just compress it, right? Because now all my inputs are half as big as they used to be. So 1 used to be where it came back down on, right? So now 1/2 is where it comes back down. And so forth. You guys with me? So it just makes twice as many of these little rectangles. I mean, it's awesome. Triangles. This one, like I think Anthony said earlier, if you put a 1/2 in there, obviously it's going to do the opposite. That's going to double it. So now it's going to have twice the range in a way, right? Triangle doesn't stop at 1, it goes all the way over to 2. There, right? I got the shape right that time. All right, anyway, so I'm trying to, on the heels of that, I like to give you some arbitrary function. I don't even tell you what the function is. I just give you the picture, and then I tell you to move that around. You with me? So I might give you a function that looks like, here, the book does it to you also, so don't tell me it's not in the homework, it's in the homework. So they'll give you this picture, and they tell you to do that stuff to it. Now again, I don't like their use of this y. They really should call it h of x. It's like a new function. Because some of those might be, there's 2 y's in the damn thing. But, what's up? So the graph of g is given. What would happen to this first guy?
Move to the left one.
Yeah, move it back 1. So every point, you just pick the points you can definitely tell. Those are like your anchor points, and you just shift them all back 1. And then you fill the shape back in. That's nice. That kicks ass. I don't have to know a base function. They give me the function. I just move it. Okay.
Cool.
Yeah. So enjoy that. I like to do that on the test. Blah, 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 blah.
Well, you will give us the initial graph on the test.
I have to. Yeah. I'll either give you the function, define it for you, or I have to give you the picture, the graph of it, and ask you to move it on. Real quick, just a little preview of the next section. I actually did want to get to, but I won't. This one I'm going to blow through a little quickly, because all this is, if you saw this, what do you think you do with the f and the g functions?
Add them together.
You add them together. That's great. And if you saw a minus, you'd subtract the functions. If you saw f, g, you would multiply the functions. If you saw f over g,
You divide.
you divide the functions. Okay, so that's, let this section 2.6 be easy. Right? It looks like it's difficult, but they give you functions and then they tell you to make stuff like
What day is it? They're testing on the 4th, right?
yeah, there's tests next Thursday. A week from today. Huh? Oh, that's right. Don't forget that there's no class on Monday.
No, please forget.
Monday's Labor Day. Don't come to campus. You'll be very alone.
On the campus.
Oh, Chris, tell me what your question is.
Chris, tell me more about your question.
What was the tree doing initially? What was it multiplying? And now it's only multiplying. But, alright. They can't become multiplication in the next step. All you do is, you don't put parentheses, you realize what's negative 5 times negative 8. And then you can know whatever the hell. Be real careful about it. When you introduce parentheses, you might entirely change the operation itself, right? That's better. That's better. The only thing here is just bring the tube through, just clean it up a little bit. See the tube can go in? Just a little cleanup. Twice 7, twice negative 3d. Just to clean the inside.
Oh, 14 minus.
Nothing major. Exactly. And that's good. Okay, cool.